Hello, good morning. So in this video, I would like to show you the working of CMOS inverter. CMOS two input NAND gate. Okay, so in my previous video, I shown you the working of CMOS inverter. So now let us see two input NAND gate, how to realize it and how it works in the CMOS uh, logic family. Okay, so this is a symbol of a NAND gate, two input NAND gate. So the truth table. So when both the inputs are high, then only the output is zero. When any one of the input is low, then output is high. Okay, so let us see how to realize this with simple switches. Then we can go to CMOS realization. Okay, so let us say I'll draw the switches. First I'll draw and let me explain it later. Okay, so two switches I need for the top network, that is called the pull-up network, and the bottom one is called the pull-down network. Okay, so let me connect the load capacitance CL here. I connect it to VDD power supply 5 volt. Okay, so I have the switches. I have the switches here, four switches. So this top one is called pull-up network. The bottom one is called pull-down network. Okay. So pull-up is for charging, pull-down is for discharge. So the network is made in such a way that to realize a logic circuit. So that is a two-input NAND gate. So these two switches, the gates, the control inputs, the gates are connected to a single input, as in the case of inverter, and I'll call it as A. This is B. So now again we should have a mechanism here that if the top switch is closed in the pull-up network, the corresponding switch in the pull-down, if top one is open, the corresponding switch in the pull-down has to be closed. And if the top one is open, the corresponding switch in the pull-down has to be closed. So this is the arrangement that is required. When one is closing, the other has to be opened. When one is opening, the other has to be closed. Okay. So now, in this case, suppose if input is given 0 volts, the corresponding switch in the output has to be closed. Okay. So this is 0 volt, 0 volt. So now this is the arrangement that I have made for the switches. The top switches are different from the bottom switches. The top switches are behaving when the input gate voltage is 0, it is opening, and the bottom switches are closing when input voltage is 0 volts. Okay. Now in this case, like when A is 0 volt and B is 0 volt. So 0 volts means it is corresponding to logic 0. Okay. So when A is 0 volt and B is 0 volt means A is logic 0 and B is logic 0. And the output has to be logic high, logic 1. So let us see how it is happening. So when both inputs are 0, 0, the bottom switches are closed. So, and the top switches are open. So, okay. Uh, Sorry. So in the other way around, actually, in the other way around. So these two has to be open and this has to be closed. Okay, when 0, 0 volts. So in that case, what is happening is there is a path for charging the output node. Both there are two paths. So both the paths are like they are allowing the current to flow, to the output node. Okay, there is a current allowed. So there is no way that the current will be discharged through this, right? The current cannot be discharged. So the output node will be charged up to the VDD. So giving that output as logic 1. Logic 1. When both are 0, 0, output is logic 1. That is logic high. So suppose if I make one of the input as 5 volt. So what will happen if one of the input is 5 volt? This switch, the corresponding switch is closed here. This switch is opened. So the current path through this is not allowed, but there is a path to the left branch for the output node to be charged. So it will still charge. But is there any way that the charge will be discharged simultaneously? No. Why? Because even though this is closed here, the upper gate is still open. Since these two switches are connected in series, unless until both switches are closed, there is no way that the current will be discharged. But the top switches, the pull up network switches, are connected in parallel. So that means that if any one of the switches are closed, there is a path for the current to flow. Any one switch is closed. Okay, so now what is happening? So since it is charging, the output node is charging up to the 5 volt, so output will be logic high. 0 1 is output is 1. So similarly, if A is 5 volt and B is 0 volt, so what is happening? The B is connected means the bottom switch is open here, the corresponding switch is here, it is closed, and A switch, this is open and this is closed. So in this case, what is happening? There is no current flow here, but there is a current flow through the right side branch. Still it is charging. Okay, so again there is no way that the charge will be discharged through the pull down network because the bottom switch is open here. So until unless both the switches are closed, there is no way that the charge is getting discharged. So that means in this case also, 1 0 case also, output is 1. So when both inputs are 5 volts, so in that case only both switches of the pull down network are closed and both switches of pull up network are open. So there is no way that the output node will be charged. If it is previously charged already, so that will be discharged through the pull down network because both switches are closed here. There is a path. There is a path for discharging it. Okay, so that means output, if it is high initially, that will be made logic 0. Okay, so if both inputs are 1 1, output is 0. So that is how we realize with switches. Okay, now so as I said, as we have seen for the inverter case, so similarly here we can realize this with a CMOS devices. Like in CMOS means complementary metal oxide semiconductor. So complementary means we have PMOS transistor and NMOS transistor. So all the PMOS transistors will be used as the pull-up network, and NMOS transistors will be used in the pull-down network. Okay, so these switches are basically replaced by PMOS and NMOS transistors. So why PMOS and NMOS? So PMOS transistors and NMOS transistors, like when they're connected like this, both gates are given to the same input. When input is 5 volt, the NMOS will be closed and PMOS will be opened simultaneously. Okay, so because they behave like that, fulfilling this kind of arrangement, so we replace these switches with PMOS transistors and pull down switches as with NMOS transistors. Okay, so let me draw that here. Okay, so two PMOS transistors at the pull-up network and two NMOS transistors at the pull-down network. So we can see that there's a bubble at the gate representing that the majority carriers or holes there. That means the PMOS transistor. Okay, so now these two are connected together, and these two are connected together, and this is input A, this is input B, and from this node output is taken to the load CN. Alright, so now this is to VDD, this is VSS. Okay, now when we can see, we can see the analogy of this. When input A is say 5 volt here and B is 0 volts, what is happening? This particular NMOS transistor will be on. Okay, so VGS corresponding to this node voltage, it is positive, so this NMOS will be turned on. But here VGS is 0 here, this is not on, this is off only. Okay, so there is no way that there is no discharge path. So what is happening to the pull-up networks when 5 volt is given to A here? So this transistor, PMOS transistor, is getting VGS. This is a gate to source. This is also 5 volt. When it is 5 volt, 5 volt. So this will be turned off actually. VGS is 0. And whereas the B case, it is getting 0 volts here. This is 0 volt. This is 5 volt. VGS, gate is 0 volt and source is 5 volt. So gate to source is minus 5 volt here. Okay. And this point to this, the drain to source is also negative voltage. So there is, it will be turned on. So there is a current path like this. The current will flow from VDD to this load capacitance. It will charge. It will charge up to 5 volt. Okay. So that means making the node to logic 1. Like, this node will be pulled up to 5 volts. That is logic 1. 5 means this is logic 0. This is logic 1. And this is 0. When 1 0, 1 0 case, output is 1. So if it is 0 1 case, also the same thing will happen. The output will be 1. When both inputs are 0 0, what will happen when both inputs are 0 0? These two NMOS transistors will be turned off. There is no path for the discharge. When this is 0, this is 0. VGS is minus 5 for both the transistors. So both PMOS transistors will be turned on. PMOS will require negative voltage to turn it on. As I said in the inverter case. So we are not having a negative power supply, but it is relatively negative. The gate to source is 5 volt plus 5 volt, and gate is 0 means VGS is minus 5 volt. VSG is plus 5 volt, and VGS for PMOS transistor is negative minus 5 volts, making the PMOS transistors turning on. And for the current to flow, there should be a negative voltage from drain to source. Since the drain is less than 5 volt, so there will be a VDS for PMOS transistors, drain to source, which is relatively negative. So causing the current to flow from VDD to this node, which is connected to the capacitor. Okay, so making, when both the transistors are turned on, again there is a path for charging the network, charging the output node through these two branches. But there is no way that it will be discharged. Okay, so the output node will be charged, and then you'll get a logic high when it is 0 0. Similarly, when it is 0 1, it is 0 and 5 volt. So in that case also, when it is 5 volt, this transistor is turned off and this is turned on. So there is a path for charging, but there is no path for discharging. Why? Because even though this is turned on, this is off. So there is no way that the current will be discharged. So only charging path is there. So for the charge to be discharged, both the inputs have to be 5 volts. That means making both pull down transistors and MOS transistors turning on. So both transistors will be on. So then only it will be discharged. So during the discharging, there is no charging. Why? Because both the transistors, PMOS transistors, will be off when A and B are 5 volt, making VGS 0. VGS of PMOS 1 0, VGS of PMOS 2 is also 0. So that means there is no way that the output node will be charged. Okay, so that means only discharging is there. So when 5 volt, output is discharged to 0 volts, making it logic 0. So it makes, this simple CMOS, complementary MOS, is making your NAND gate operation. So upper one is called pull-up network. This is pull-up. This is pull down network. Okay, so the CMOS circuits are mainly complementary or inverting circuits. Naturally, we'll get the inverting output. Okay, so we have the AND gate. AND gate means output will be high only when both inputs are 1. That is AND operation. So to get an AND operation, we have to pass the output through an inverter. Okay, so naturally we are getting a inverting operation, NAND operation. An inverter also, one PMOS and one NMOS connected, that is giving an inverter. Okay, so that is how we realize the NAND gate here. So see you. So in my next video, I'll show you how to realize a 2-input NOR gate. Okay, see you.